Hello, my name is ALLA SIDHKO, and I represent the Faculty of Informatics of the National University of Kyiv-Mohyla Academy. We propose to use the supercomputer platform developed by us as one of the tools of the Open Science project. Next, I will talk about its benefits. Modern supercomputer systems containing hundreds of thousands of cores face difficulties in the organization of parallel computations. The three main difficulties are the non-uniform hardware workload, accumulation of errors in the process of computations with large matrices, and possible failures of cores during the computation process. A new software infrastructure for organizing distributed computations, which can be called a supercomputer runtime environment, should be created. Such an environment should support the development and efficient execution of programs on modern clusters. Today, when we live in the era of big data, it is important to expand the size of problems that can be successfully solved. We propose the creation of another component of the open science infrastructure in the form of access to a supercomputer that supports a special library for matrix algorithms. The library will work with a new runtime environment for tasks execution on a supercomputer with distributed memory. This environment is designed for recursive matrix algorithms for both dense and sparse matrices. It provides dynamic decentralized control of the computational process and significantly expands the size of matrix problems that can be successfully solved. In this environment, such matrix algorithms as matrix multiplication, finding the inverse and pseudo-inverse matrix, QR and LU decomposition of matrices, the Cholesky decomposition, finding the joint matrix and the kernel of a linear operator have already been implemented. The SVD algorithm is also being developed, which is actively used in recommendation systems. This mechanism can be applied to any recursive algorithms with both dense and sparse data. The new control scheme is called the DAP scheme. Its main difference is that it sequentially deploys functions in depth, saving all states at any nesting level until all computations in the current computation subtree are complete. This mechanism allows any processor to switch tasks without waiting for the current task to finish. It can be used only for block recursive algorithms, and in such algorithms, independent separate subtasks are applied to blocks. So it is easy to organize decentralized control over the entire computational process. In this slide, we can see the example of the graph of the block recursive matrix multiplication algorithms. And the first step is that we have two input matrices A and B, and we need to do matrix multiplication. So we divide these matrices into 4 blocks. And after that, we send these independent blocks to the different processors on a cluster, and we can do all computations independent in parallel. After all multiplications, we gather block results into 1 matrices and return entire result, the matrix C. In the next slide, we can see example of the graph, the Cholesky decomposition. And here we have the same blocks with different operations. For example, this block with matrix multiplying, as in the previous slide. And in the right, we can see an example of the connections between these block operations in the graph. First number, it is the number of dependent block operation. Next, it is a position to write from output data from block operation, and next it is position to write to input data to the dependent block operation. And the protection in case of node failure during the computational process is an important feature of the execution environment. The parent node that sends the data to the child node should receive the result. However, it may receive child failure messages. In this case, it should forward this task to another node. No additional changes should be made on other nodes. Only one subtree that matches this data will be lost and recomputed. This scheme was implemented using the Java programming language with specification OpenMPI for communication between processors on a cluster, and using matrix libraries called MathPartner. We conducted a series of experiments, and these experiments demonstrated the advantages of the new runtime environment, in particular good scalability. The experiments were performed for 3 algorithms: multiplication of matrices, inversion of triangular matrices, and Cholesky decomposition. Special series of experiments were performed for double precision and big decimal data. To give a numerical assessment of the scalability of the proposed solutions, we use the term of transmission loss ratio. We carried out the experiments with matrices, the size of which doubles. Then the number of machine operations increases by a factor of 8. Correspondingly, the number of cores was also increased by a factor of 8 for each matrix size. If the data transmission time were 0, and there was no time loss due to non-uniform workload of the hardware, the computation time would be constant and equal to 1. On the other hand, if the number of operations doubles and the number of cores also doubles, but the computation time doubles, then there is no scalability. The transmission loss ratio is defined as the coefficient of increasing the computation time, where T2 is the computation time required when the number of operations increases by a factor of 2 and the number of cores also doubles. This coefficient should be in the range from 1 to 2, and scalability is characterized by its closeness to 1. This table presents the results of 3 series of experiments carried out on the cluster. In each series, a constant computational load per one core was maintained. When the matrix size doubled, the number of cores was increased by a factor of 8. Big decimal numbers with 100 decimal digits in the fractional part were used. It is seen from the second row in the table that as the number of cores increases by a factor of 8, the computation time increases by a factor of 3.0, then 2.4, and 2.2, respectively. The corresponding transmission loss ratio is 1.44, 1.35, and 1.31. This data indicates good scalability of the proposed software solution. We propose to connect our supercomputing execution environment to the open science platform and make it available to all researchers. Since Ukraine does not have its own high-performance supercomputers, international cooperation is needed to create such an open science infrastructure. It is necessary to create a joint team together with those organizations that have supercomputers of great power and have scientific teams working in areas close to ours. Our aim is to find partners who are interested in creating a joint team. Thank you for your attention, and I am ready to answer your questions.